he'll give the talk on processing, right? This is going to be a really nice workshop, we hope. And to the people who are saying P5JS, spoiler alert, it is happening very soon. Thank you again for coming on this possibility.
Okay, so good evening everyone. Processing is a very addictive language. It was my first language I ever learned, and till date it does not burn me out even if I put it in for like no matter how long it takes to make something, to complete something. So what is processing? Why are we not considering any other languages? There are hundreds of languages. Java. No, you cannot hear me now. Hello? Hello?
Keep talking.
Fine now? Yeah. So, processing is a very different language than what we usually learn because it is not made for general purpose computing, not made for scientists, not made for engineers. It is made for artists primarily. It started as an open source MIT project around 2001 and matured around 2004, and it has been being developed ever since. So I will tell you why we choose processing today instead of other languages. So processing is a wrapper around Java basically, but it takes out the pain of Java. If you ever use Java, you know how important it is to never use Java. And in coding process, if you code in processing, you can easily spend like 3 or 4 years even without using the fact that it is Java. You don't need to know Java to know processing. Although it was created for creative coding like drawing with code and mathematics, artistic coding basically, it can also do scientific visualizations very efficiently. So, in fact, that is something that inspired me to take on processing. But again, why would you use it? Why would you choose to use it? First of all, is the ease of using processing. It probably takes the least amount of code to get started in processing. You can just write 5 lines of code and draw something on the screen. No language has this amount of ease to get something drawn on the screen. If you use like Python or Matplotlib, you need a lot of preparation to just draw simple stuff. Processing does not need that. It has all the stuff built in for it. So you can start pretty quickly in this thing. But also, usually in easier languages like constraint processing, it is pretty different because it retains some low-level power. So if you want to go down deep into the program, deep into the memory allocations and all, you can do so. You can do so pretty easily. And since processing is basically a wrapper around Java, you can just code native Java code and add it to processing if you know Java. But it has one downside that I would like to consider, that tweaking the libraries is not so easy as in Python. Like in Python, you can just Ctrl+C can go to the library and tweak it to your needs. You cannot do it in processing. Most of the libraries are compiled there, and you need to compile the libraries before, after you edit them. But also, a big advantage is making an application out of processing is very easy. If you have something that you would like to share with your friends, you can just export it as a exe file and pretty easy, very easy. You can do it in other languages also, but it is exceptionally easy here in processing. So this is the ease of use, but ease of use is not enough for most of us. We also need speed because in scientific computing, there's a huge lot of calculations to be done, and processing SS here also. It is it's about a couple of orders of magnitude faster than Python in most cases. But of course it is about 10 times as slower than C, but the libraries that we have in processing to perform your calculations, you can get basically like almost as fast as C, as fast as it gets. Processing, like the backend of processing is OpenGL, which is the Open Graphics Library. It has been in development for a long time. It's very polished. It's a very powerful backend processing, and it is extremely fast. I will show how fast it is in some time. And also you have other libraries like ToxicLibs, Ketai, OpenCV, and Puro. ToxicLibs is a physics library, so like physics engine. So you can use it to make games in processing. And not very like, not ridiculous games, but pretty good beginner games. Ketai is used for getting data from sensors, like in our Android phones. Ketai can pull in exact, very accurate information about the GPS module, accelerometer, and gyroscopes. And OpenCV is Open Computer Vision. It is usually used for computer vision algorithms, and it is extremely powerful in object detection. It is extremely simple and powerful. YOLO is also a machine learning library for object detection. So this is speed, it's pretty fast. Now, many of you don't know Java, or if you are like me, you hate Java. So, but that does not stop you from using processing, because you can write processing Python syntax. It's Python 2.7 syntax, so it's pretty old, but you can do it. And in fact, processing does not remain limited to Java syntax. It has many different modes. So you can write processing in Pythonish syntax. You can write it in JavaScript syntax, which is a separate spin-off project of its own called P5.js. And P5.js, we are going to have a talk on P5.js pretty soon from Turing. It's an extremely powerful library, and there is a plethora of internet resources on P5.js. I will show you one P5.js site soon. And the advantage of using P5.js is once you get to the browser, you can deploy it anywhere in the world, and also you can use a variety of libraries like ML5.js, which is a very powerful machine learning library built upon P5.js, which is built upon processing. It has also a very powerful Android mode. So you can make Android apps in processing and directly install it in your phone. It does not stop there. You can make live wallpapers. You can make VR headset inputs in processing, and even smartwatch cases like the smartwatch. Smartwatch wallpapers. It has other modes also, like the R mode for statistical analysis. The REPL mode, it has not been in development for a few years, so let us use it. And it also supports Raspberry Pi without any major porting issue. So you can just copy your code from your laptop and run it in Raspberry Pi quickly. It is a pretty influential language. If you look up the list of used languages in internet, processing does not come in the first 100. But it has a large influence than some languages that does come in the first 100. Especially it was influential because of the artistic side of it. The artistic goal it was made with. And it has heavily influenced the Arduino language. So processing works very well with microcontrollers. You can directly communicate with microcontrollers for processing. And the biggest advantage of processing, in my opinion, is the learning curve. It is a very steep learning curve. It is extremely great for beginners. Many of us started coding with processing. Even if you know Java, even if you know what is programming itself. It has a very helpful community, very welcoming community, and it has extremely large database of examples. That is very helpful for beginners because examples are 100,000 words, right? So I will just open up processing right here and show you the examples, how it ships. So when you open up processing, you will get this welcome screen. So this is your text editor. You write your text here, you run your text here, everything is here. And if you go to file and examples from above here, you will find a lot of examples in different topics. These are very helpful if you are starting out with processing and does not want to know what are the features available for processing. Apart from all these parts, the biggest thing that, in my opinion, defines processing, separates everything, it is extremely beautiful. So you can make your graphics very beautiful, very quickly, with some minor tweaks. But what will you use it for? So it depends a lot on what you want to do. So you can do generative art, you can draw with codes, you can draw with your mathematics. You can do game development here, simple games. It is a very nice platform to get started with game development. You can make scientific simulations here. This was not one of the goals of processing, but it has over all these years been developed into a very powerful, not a very powerful, but a decently powerful simulation language, and it can do a lot of things very simply that requires a lot of code in Python or other languages to start with. One of them is object detection. So suppose you are trying to detect posture of a human, and you detect the position of my hand or face recognition. It is very easy to do it in processing. Even getting the simplest thing started in Python takes a lot of code. It does not take so much in processing. You can there are examples. There is very short lines of code that you can use to get started, but again, it gives you an opportunity to get deep into the program and do whatever you want. So that's the overview of processing, what it is and why you use it. But enough talking, let's just see some examples, what you can do with processing and what is the possible things you can imagine out of processing. So this is the processing website. It has excellent documentation, and this is the processing website for Android. So these apps are available in Google Play. I will send you all the things after the talk. I will send you over mail. There are amazing games you can make in Android. There are graphics, there are physics engines, small physics engines, simulations that you can do in Android and export it as apps. Extremely simple. And this is the watch face I was talking about. You can make these simulations in your watches. And so the source I would recommend you to learn processing from is this book. It is called The Nature of Code. It is written by Daniel Schiffman, who is one of the main developers of processing. It's an excellent book. It covers a lot of subjects, especially in physics, and it does requires fractals, cellular automata, and so on. And it is written absolutely for beginners. You can suppose I can go into the fractal page and show you. He has hand drawn this picture, and it's a very lucid description of what fractals are. And so you can learn processing from here. It's very much recommended. There is another book by Daniel Schiffman called Learning Processing. You can use this also. But now let's get into examples. So I talked about P5.js, which is developed over processing, so JavaScript. So there is an excellent website called Open Processing, where people generate all sorts of creative stuff and just put it here. It has a collection of extremely beautiful generative codes. So what you can do is you can open up this site, open up anything that you like, and you can edit the codes right there and run it in your browser itself. So you need not download anything, but it is JavaScript. So it is helpful to have either knowledge in JavaScript or processing. So we'll start with processing today. You can also search up processing generative GIS in your browser, in your search engine, and get all sorts of creative stuff that people happen to make. Most of the things are extremely beautiful here. And these are all generated by processing. You can also generate pretty pictures with pure mathematical equations. Like yes, so these are some of the like abstract art generated by these equations are written down here. And it is extremely easy to do all this in processing. If you want to generate such high quality images in other languages, it will be a pain. You can also generate images like this. These are called Samila mappings. These are generated in processing. Extremely beautiful again. And then you can also work with physics engines. This is a physics engine simulation of an E filled with letters which rolls and falls down. You will see that it spawns the letters, fills up the character E, then it topples over the E, the gravity changes. So this is a demonstration of the physics engine libraries that you can use in processing. I will, talking about speed of processing, I will show you one demonstration of how fast it is. So what you are seeing here is 3D slices to a 4D attractor. It's a chaotic map, and this thing is rendering 60,000 points per second, 60,000 individual points per second, and coloring each of those and generating this image. If you want to do it in like Matplotlib, good luck. It will probably take a PhD in Matplotlib. And the most surprising point of this thing is to generate this whole thing that it is being live rendered. It takes only 39 lines of code, and probably 10 lines is just blank space. So you get an idea of how easy it is to just get things drawn in processing and get pretty visuals out of it. I have some open processing examples. Of course, you can replicate all of these in processing itself, but these are written in Java. So this thing is like a galaxy, I would say. It looks very pretty. And you have wait one second. Let me just change the values a bit, it will look nicer that way. So what you are seeing here is called a Parley noise flow field. Usually when we have talked about random number generators, it's usually Gaussian, Poisson, or just uniform random distributions. But there are other kinds of random number generators used in game development, especially like terrain development and drawing a sea or a water body. It is kind of random, but you can see these very smooth flow fields in here. It is called Parley noise. So processing has built-in support for Parley noise, and you can use other noise also like open simplex noise. It is hard to believe that this thing is random, actually. This is another very brilliant code I have ever seen. So it starts out as absolute gibberish, and as you let it develop, you can see a person's face forming out. So this is what processing does. It makes stuff very beautiful. Another one is this canvas. It draws small lines in the canvas to make these spotsy canvas. I don't know what to tell this.
It's like how a bacteria is like it's like how a bacteria is like
Yes. You can make also doodles with processing, and this is a random snake generator. It generates random snakes. Each of them is what we call them. This is a physics simulation. It drops small colored grains of sand to draw an image. It is dropping these colored grains in the perfect places to develop this image. It will take a long time in my computer to do so because my GPU isn't powerful, but you get the idea how it looks like. This is another simulation processing again. Beautiful. Oh, my GPU will die now. I cannot show it in my laptop. But it basically fills the whole screen with these colored blobs. Colored blobs. And we also have this, yes, now I have to just resize it. This was used in like billboard I guess, advertisement in Japan, and the whole thing is live rendered in processing. It is not a pre-rendered video. You can put all the stuff you like here and pre-render it out. Everything is mathematics here. Nothing is hard-coded. Hard-coded in the terms that pre-rendered, not hard-coded, pre-rendered. So that was what, more or less what you can expect from processing. Now, yeah, it looks fine, okay, but let's make something like that. Let's make a code in processing that will draw a snowflake. Because we figured out that sitting here for an hour just looking at the syntaxes and how easy to telling that how it is very easy to use it is not enough. We will code snowflake generator right now. So let's keep this aside. Let's go to snowflakes. One second. Okay, any questions till now? Anything you want to ask? Okay, I'm moving on now.
Can you switch off those lights? Like they are blocking the project of you.
Are you fine?
Okay, so now a little bit of snowflake physics. Snowflakes developed by a process called WBF process. I don't understand the word of it. I will give you the Wikipedia link, you can just look it up. So, how we are going to draw, like how is a snowflake formed basically? So you have a seed in your ground. You have a small seed in your ground, a small particle, maybe a bacteria or a particle of dust. Now your whole ground is supersaturated. It has water vapor, water molecules that are not in solid or liquid state, these are gaseous form, but their temperature is much lower than 0 degrees Celsius. So the whole thing is supersaturated. The water molecules is just trying to find some nucleation point and getting attached to it. Okay. So how snowflakes usually develop is you have a lot of water molecules and those go into a random Brownian motion. Okay. Those like go around like this, and once it happens to meet something, existing nucleation particle or a existing ice particle, it instantly sticks to it and stays there. So the water molecules stick like this and stay there. So this process is known as diffusion-limited aggregation. Soft non-instrumental people might know about it. It is found everywhere in nature. It is found in rock formations, snowflakes, crystals. Everything forms in this way, diffusion-limited aggregation. So ideally, what we can do is we can simulate this whole thing. We might have a nucleation point and we might generate many water molecules and put all them down in motion and develop it through time and see how it is forming. So yes, this is DLL. This is like what we are going to do is falls under the purview of a wide range of algorithms known as diffusion limited aggregation, DLL algorithms. So so the code we are going to do is a simplified version of Daniel Schiffman's code. You can find in the Coding Train YouTube channel. I will send the links. Daniel Schiffman's code is a simplified version of a mathematical code, and it itself is a simplified version of the original paper in 2003, which dealt with how snowflakes actually form.
That process, regular background understanding.
It's a DLL process, diffusion limited aggregation. Yes, were you asking something? No. So I will not go deep into the syntaxes of processing because you will need it. You can just look it up in internet anytime you like. All you need to do is you need to just remember, okay, somewhere I like heard this thing that processing, there is something in processing that can do this, that can draw a line, that can draw a point, that can shift the coordinate axis, and you can look that up. So the important thing is knowing that you can do it in processing, not exactly knowing what does it. So I will not explain the individual syntaxes in detail. I will just go over the whole picture and explain everything in the way. You don't have to worry about remembering everything. You can always do it later. So let's start. Processing code. The structure of processing code is very simple. You have can you hear me? Okay. So you have two broad parts in processing code. The first part is the setup part. So the setup part deals with what setting up your code, what you will run only once. So suppose you want to load a picture, you want to draw a background, you want to define this nucleation point. So all this stuff we will do in the setup. We don't want to define many nucleation points, we will just do one. So setup draws the nucleation point, and setup first creates the canvas. So the way you write it is void.
File phase setup. File phase setup. Here we
So this void setup, inside these two brackets, you put everything that you need to run only repeat once. So the first thing we would like to create is we would like to create a canvas, is a screen which is called a canvas, which will contain all our drawings. So we will create a canvas of size 600 by 600 pixels, and let's just run it first and see what it does. So it has created a canvas. This is a blank canvas. This is the basic things on which you will draw. We will draw everything. So this is 600 by 600 pixels. We got our canvas. Now we want to set the background color of our canvas. So the way we do it in processing is just background. So you can see a background 0 here. This 0 is the color of the background. So how do we represent colors as numbers? Processing supports RGB and HSL color schemes. So you can define a color in terms of the individual components of red, green and blue the color contains. And also if there is only one number in your background, by default processing takes it as a black and white image with that amount of brightness. So 0 here means it is totally black. It goes up to 255, which will make it completely white. So now our canvas is completely white. If I put it 0 here, that means it will be completely black, dark. So we have got our canvas and color. The
method to get a different color.
what?
Can you repeat the method to get a different color?
Yes. So we can tell a number between like
No, in RGB scale.
what?
This is a black and white, right?
Yes. I'm coming to that. So suppose you want a cyan screen, right? So this is RGB. So cyan would be something like 100, 50, 120. So if I run it, you will see the background is cyan. Okay. So there is another variable you can put there after you have put your color. That is called the alpha of the color. Alpha of the color is a transparency of the color. So I will show it here. Alpha is extremely important in processing because it gives you a way to not erase what you have already drawn. You can put an overlay on what you have already drawn and build upon it. So I will just put it 0 for now as we go along. So we have made our canvas. This is fine. Now what we will do, we will introduce the void draw. So the setup is run only once. So whatever happens in the setup is run only once. Now the next part of processing is draw. So whatever you put it in draw, it gets executed over and over again in a loop in each frame. So whatever, when it completes going through the draw once, it will generate a new frame. And it does it over and over again. And we usually put our global variables up here. So the basic setup of a processing sketch is variables, setup, setting up a code, and draw, which is kept drawing. Which is each new frame is drawn over and over again until it is ready to stop. So now we will make our seed, the nucleation point on which we will do our random. So to make our seed, we will draw a circle in the middle of the screen. So there is no separate function as circle processing. The function is called ellipse, and the first two arguments that ellipse takes is the center of the ellipse and then the major and minor axis of the ellipse. So I can put like say put an ellipse, draw an ellipse at 200x and 200y with radius 5 and 5. So it will be a circle centered in 200 axis. So that brings us to how processing deals with axis, the coordinate system of processing. Yes, sir.
What's the range of the size we can provide and what if we don't provide size at all?
Size you need. Without the size, the program will not run. So, and the size, the pixel size you can give, the canvas is unlimited. You can make any size of canvas you want. It can be even bigger than your screen. It can be full screen, it can be bigger than your screen.
Can you explain the 4 parameters in the ellipse again?
Yes. So the first 2 parameters are the center of the ellipse. I will tell how that is figured out. And the next 2 parameters are the major and minor axis of the ellipse. Okay. So we are drawing a circle here. So we are putting major and minor axis equal 5. So processing the canvas, if this is your canvas, it does not use the right coordinate system. So usually what you will expect, this is the origin, this is 0, 0. And then you go positive y and positive x. Processing does not use this canvas. What processing does is it takes this point as its origin, 0, 0. And this axis as a positive y and this as a positive x. So 200 means from your left upper corner of your screen, move 200 pixels x and 200 pixels y to get your center of the ellipse, and then draw an ellipse with a radius of 5 pixels. So when I run it, you can see this small spot here. Let me increase the size of the ellipse. So let's make it 25 by 25 radius circle. So that is your circle, 200 pixels from the top and 200 pixels from the left. So what we do is we will put a nucleation point exactly in the center of the screen. So the center of the screen will be the width of the screen. Width is a keyword in processing. So as soon as I write it, it becomes red. So it knows width means our screen width. So at the center of the width and at the center of our height by 2, we will draw an ellipse. So here you go, it's centered in the width and height. Instead of putting directly 25 here, I will make a variable and make it the radius variable. So let's define a radius variable in processing. Now, unlike Python, at least in Java mode of processing, you need to define what kind of data type you want to use when you are defining a new variable. So you have to specify that okay, the radius variable I want should be a float. So I am defining a new variable, new float variable called radius, which has a value of 25. We initialize the variable. Now if we replace 25 by rad here, we will get the radius there. So we got our nucleation. I mean, the nucleation point is perfectly white now. I will give it a little bit of transparency. Why we will come to it later. It will look good, that's it. So we will give it a little bit of transparency. So I will fill it with white, fill the ellipse with white and 80 transparency. And when we run it, you will see this slightly dim ellipse because it is slightly transparent. The background is black, so a white transparent thing looks grey on it. And there is another command, no stroke here. No stroke just means that we will not draw the edge of the ellipse. It will, we will just fill the ellipse. Okay. These no stroke and fill commands are remembered by the processing until we change the feel to be different or Brownian motion. So what we will do is in each frame we will add a random number with the x coordinate and a random number with a y coordinate. So let's make our random one. So I will introduce a parameter here called dizziness. Dizziness is the mean free path of the molecule, how much it will go around. And with the x coordinate, you will add a random number between minus dizziness and plus dizziness. So it will add a random number between minus 5 and 5 with the existing x coordinate. So now let's see what happens.
Is processing case sensitive?
Yes.
So shouldn't the stroke has a capital S?
Well,
No.
no. So no stroke has capital S, and this stroke is the keyword. It does not have capital S.
Oh, okay.
So if I change it to capital S, it does not. It shows an error.
Why does it no stroke has a capital S?
Because the convention in Java is whenever you have two words, like two human words, one after another, instead of putting a underscore,
Okay.
we put it capital so that we can read it.
Yes.
Yes, so that it is readable. So now when we run it, we will see a tiny water droplet roaming around in a Brownian mode. It's hard to see that. Can you see that? So that is our Brownian motion, random one. It is going around, just roaming around.
We can change the color of the part to white, right?
Yes, we can. Why I am not doing that I will come later. For now, let us think that it is a water molecule, it's aqua color, it looks good. Okay. So now we have nucleation point, we have our water molecule that is going on in a Brownian motion. Now, making the water molecule just in the center moving around random is not very helpful. So because water molecules does not exist in the center of the droplet, so we will throw the water molecule from our left side. So I will initialize the position of the water molecule as x is 0. So now instead of starting in the middle of the screen, it will start at the very left edge of the screen, in the middle, in the y direction. So if we do that, we can see our water molecule here, right here, but it will take a lot of time to actually get to the nucleation point and stick to it. That is not feasible in computer simulations. So what we will do, we will give it a little nudge towards the center, so that it moves towards the center and not just roams around. So neat way of doing that is instead of taking a random number between in the x system, instead of incrementing it as a random number between minus 5 and plus 5, we can just decrease the chances of it going out from the screen. So we are increasing the chances of it going towards the nucleation point. So now as we run it, we will see that our water molecule starts from the middle and goes towards the center. Okay, and it keeps going and exits the screen. We will take care of that later. But now we have got our water molecule which is moving in a pretty random way towards our nucleation point. In reality, Snowflake does not care about water molecules moving towards the nucleation point. It just happens randomly. It is not possible in computer simulations. So now we have got our water molecule and thrown it forward. Now we have to stick it because it just does not care about the nucleation point. So how will we stick it? Here comes the cool part of processing. Notice that we are not using any arrays to store the information of how much, like where the nucleation points are and where they are. What we will tell instead is, okay, you have a nucleation point or a small snowflake, whatever. As soon as the water molecule is moving, as soon as the water molecule sees ice, so as soon as it attaches to something that is white, something that has ice, either an equation point or some snowflake, it will stick to it. So now how do we get that, okay, there is some ice there? In our canvas, we have everything is black, only the nucleation point is white, so it is not perfectly black. So we can say that, okay, whenever our water molecule is at this current moment, find the brightness, find the color of that pixel. If it is black, then there is no ice, you keep on moving. If it is not black, if it is white, then you stop it. The problem is that we have a trait also, which is cyan. So I will specifically say that, okay, if there is a red component in the position you are in, the pixel position you are in, then stop there and become ice. Okay, become white. So what we do here is in the void draw, we are getting the position of our particle. We will say that get the color of the pixel that you are currently in. I am using round because the get function, which gives us the color of the canvas at that particular point, unfortunately does not take float values. Since x and y are float, I am converting to integers. So get the color at that point and extract the red value of it, because cyan does not have any red, black does not have any red, white have red component in it. So I will get the red out of it, and if the red component is not equal to 0, then what we do is we draw an ellipse of the same radius, the nucleation point radius, because it's big. We draw an ellipse at the current x and y position, which will be white. It will be white because I have said earlier that you have to fill with 255-80 color, so it is transparent, slightly translucent white, and processing remembers that. So you don't have to specify that one another time. We will just tell that draw the ellipse. Now let's see if it collides. Yes, so we saw it colliding and it becomes an ice droplet, but it keeps moving on. So we have to stop it there. We have to stop it there. So how we stop it is, instead of stopping it, we just initialize the point again on the this point of the screen where it starts again. So what we do is we reset the x and y as 0 and height by 2. So when we run it, as soon as the water droplet hits it, it freezes there, makes it white, and then a new water molecule is created on the far left side, and it keeps moving on again. Now, if you look closely at these ellipses, the new ellipses that form, has a faint cyan border. That is because I have mentioned stroke to be cyan. Now stroke means the border of the ellipse. So before drawing the ellipse, I will just say that, okay, don't do stroke here. So I will just do no stroke. So now when we run it, we should see if it happens to stick to it. No. So we are looking at this. As soon as the water droplet hits there, it forms ice and it sticks there. Now as new water molecules come, as it sees the ice, developing ice, it sticks to it. So we have done it. Now another problem we need to address is that what if it does not even touch the circle, it just goes on and on forever. And after it has gone beyond this visible point, it is pretty useless because it is never going to come back because I have given it a push on that side. So what we will say that if the water molecules, so I have the position, if the water molecule, the x coordinate of the water molecule happens to be more than the width of our half of the width of a scale, that means it has already gone beyond our nucleation point. We don't need it anymore. So we will reset the position to its initial position. So if the x coordinate is more than width by 2, we reset to our initial position. Now let us see. It is going and sticks, and if it does not stick, it resets that from here. It starts all over again and just hopes to stick to something. So now we have our water molecules, we have our nucleation point, we have the water molecules accumulating into a ice ball kind of thing, which can then themselves become the new nucleation point. But up to this point, it is just a ball of ice. It is not a snowflake. So the six-fold symmetry in the snowflake that defines a snowflake forms due to the crystal structure of ice, and I guess only the crystal structure of ice. And all the 6 arms of a snowflake are self-similar because they form in the same conditions. As you will see, the mean free path, the dizziness parameter we have put in our random walk, defines how the snowflake will look like. So, now what we can do is ideally, we can throw a lot of these points from all over the place and make the snowflake to grow. But that requires a heavy computational load. So what we will do instead is, instead of throwing the particles around, a pretty standard simulation trick is if there is some kind of symmetry in your system, you don't bother rendering the other stuff. You render only one part of it and then you copy the other stuff. So suppose this does not only works for like spatial symmetries like this, you can also have fractals in which you just render a unit, zoom out, copy it, and then the whole unit copy it over and over again, zoom out and copy it, and so on. We don't bother rendering the whole thing. So what we will do instead, whenever water molecules happens to stick to something, we will assume that something like this happens in all the 6-fold symmetries. Okay, so this is our nucleation point. If the water molecule, suppose this is a tiny snowflake. If a water molecule happens to stick here, we will assume that it also, something like that also happens in all of the 6 positions. So we will stick a similar water droplet in this exact position in 6 places all over the 6 places, and since a snowflake has also symmetry about its arms, we will also stick one on this side and one on this side. So there isn't an easy way of doing this except trigonometry. Natively seeing where the water droplet sticks and then drawing 6 water droplets above the center by 3 degrees apart. So here comes the power of processing. That you can move your coordinate axis. You can move your coordinate axis, you can rotate your coordinate axis. So what we will do instead, our coordinate axis is now at the edge of the screen. What we will do is we will move our coordinate axis in the center, abundant equation point. So our coordinate axis is now like this. And we will see that the water molecule that was here, that stuck here, what is the coordinate of this water molecule in this new coordinate system? We will find that, and we will rotate the whole coordinate axis by pi by 3 and draw. So now our coordinate axis is rotated by pi by 3, and we get the x and y coordinates of this point in this new coordinate axis, and we draw the new point in the same x and y in this rotated coordinate frame. So what we have here is 2 points exactly rotated by pi by 3, and we will do that 6 times 2 pi rotation. So to create 6 such points, then we come back here, then we reflect. So when we rotate the coordinate axis by 2 pi, we get that this thing. This point was there. Now to get the mirror symmetry across this axis, we reflect this point about its y here and then rotate it again and draw the points again. So instead of drawing a single ellipse, what we will do is we will say that, okay, now we need to translate our coordinate system to the center of the screen. So width by 2, height by 2. Now this is our new origin line. We need to find the coordinate of our particle in our new origin. So now our x and y coordinate is this in our x minus width by 2 and y minus height by 2 in our new coordinate axis. So we have got this coordinate right here. Now since we have got the point coordinates, we will draw the ellipse at the current x and y. Then we will rotate our coordinate axis by pi by 3, and we will do this 6 times. So 1, 2, 3, 4, 5, 6, and we come back to the initial coordinate systems. So now when we run it, we should see 6 snowballs forming when one water molecule decides to stick. So asymmetry 6 points form. Okay. But this is now 6-point symmetry. I also need symmetry about my axis. So what we will do is we will reflect the y coordinate about the axis. So our new y coordinate is minus y. Now we will do the same thing again. So now when we run it, we should see, yes, 12 points forming symmetry about the 6 axis. So again it is forming a snow blob now. We will see how it converts to a snowflake soon. So this 6 ellipse, rotate is pretty messy. So let us put it in a for loop. I will not explain the syntax of a for loop right now, but so the for loop goes something like this. So for I declare integer I with an initial value of 0, and as long as the value of I is less than 6, I will keep incrementing the value of I by 1 each time is much cleaner now. And as scientists, we need to write clean code, because I have seen some code bases which are like absolutely unreadable, and I don't know how to use that and why. What was the thinking when they wrote that? So we have a clean code. Now we can clean it up even more. So it is now clean, but it is pretty non-inclusive. Like if read this, then do this, then do for loops, you can understand what is going on. So what we can do is we can pack this whole thing in a small function. Yes, sir.
Like you said that you are taking reflection about the axis, then you are rotating it.
Yes.
So in this, which command is taking doing that reflection part?
Reflection, yes. So reflection is doing this thing. So our new y is minus y right now. So it is being reflected above the x-axis right here. So it is reflecting, then doing that again. 6. So the way we will clean it up is we will put this whole loop thing in a function which we will name draw snowflake. So what this void does, void means that the system does not expect any values in return. So you can have functions called like integer or float, which will give you back an integer or float. The void just does what is inside it, does not return anything, and goes away. Okay. So we will put this whole code inside a void say package, and we will name this draw snowflake. So let's put it right here. So I have put the whole thing, translate and getting new coordinates, drawing ellipses, reflecting it, and drawing the 6 more ellipses. I'll call it ellipses. This is the snow particles that is accumulating already in a draw snowflake. So I can remove this whole part from here and just replace it. So instead of this whole part, I have replaced it with draw snowflake. So now it is much more cleaner, it is much more intuitive. You see that if the point in which the water molecule is currently at, get the color of that point. If it is not, it is white. How do you know it is white? It has non-zero red component. If it is not equal to 0, that means not white. Sorry, if it is white, then no stroke, don't draw the edges of the ellipse, only fill the ellipse. Then we will draw our snowflake. How do we draw the snowflake? That goes here. Void draw snowflake. What we will do in here? Translate the coordinate axis, find our position of our water droplet in our new coordinate axis, replicate it 6 times, reflect it and replicate it 6 times again. So once we done it, we will see the same thing. That if it misses it starts from back again. If it hits the division point, it forms the ice crystals and it glows. So up to this part is the fund of diffusion limited aggregation algorithm. Usually it is much more sophisticated, but we will keep up to this part. Now, as you can see that it is pretty slow. It takes about 10 seconds to add a single ice crystal. So we need to make it faster. Now, how do we make it faster? One way to make it faster is instead of drawing all the random walk of the particles, we can just say that okay, you don't have to draw the random walks or the particles. Only when you have a new, it hits the particle, it freezes. Draw only that. Don't have to draw the whole thing. So I will put the whole thing in a while loop. That while it is not finding any white pixel. That means it is not finding any ice, pre-existing ice. It will keep on moving, it will keep on random walking. So we will put this part, instead of if, we will say that while this is 0, that means when it is aqua or black, it is not white. When it is not white, keep on random walking. When it is not white, keep on random walking. Update your x and y. Yes, of course, draw a point after you update your x and y, but it will not draw it immediately, the point. It will only draw it when a new frame is created. So once it goes to the whole draw function, it creates a new frame. So draw the point, and if it escapes, then reset it. If it escapes, then put it back where it were. If it does not find any point to speak on, and keep on random walking until these conditions are matched. Keep on random walking until you find some place to stick to. As soon as it finds the point, the coordinate of the water molecule is on the ice crystal, that is white, it will exit from this while loop. So the while condition is not satisfied anymore. So it will exit it, and since we have exited it, we will tell it to draw the snowflake now. So let's run this thing and see. So it was extremely fast, let me slow it down. So now in each frame, a single water molecule is deposited on that. Because it is doing the random walks very quickly, it is drawing the random walks together. You can see the random walks forming there as cyan lines. So now we are getting kind of like a snowflake structure, but it is still ice block. We'll come to that, how to make it more snowflakey. Now, what we want to do is we want to stop the program, because once our snowflake is drawn, we don't want the program to be repeated over and over again. We want it to stop. So we'll tell it that don't execute this draw part again and again. Listen.
Why are we getting different pattern every time we run?
Because the random walks are random. So now what we going to do that, okay, when you have drawn a snowflake, sorry. Okay, so now we tell that when we have completed drawing a snowflake, completion of drawing a snowflake we will define as when the last snowflake touches the edge of the screen. So when the x of the snowflake particle is less than the radius, then no loops. Stop your looping. Stop the draw loop you are drawing. So stop your execution. So now when we run it, the program stops here. So we have got the physics right. We have got the snowflake algorithm correct. This is the basic of DL algorithm. We are getting 6-fold symmetry patterns, which are morphologically similar to the snowflake, but it still looks like an ice block. Why? Now comes physics again. That our radius, the radius basically is, so dizziness parameter here defines the mean free path of the random nodal axis. Okay. So it is going on average 5 units, is on going 5 units per random walk. But our it generates an ellipse of 50 radius around it. So what does it mean? It means that whenever another water molecule comes within 50 units within that particle, it will stick. But that does not happen. It will only stick when it comes to within the mean free path of the particle. So now what we will do is we will decrease the radius of the ellipse equal to the mean free path. And as soon as we do that, we are getting our snowflake. This is our snowflake. Okay? Looking nice now? We still have, you can see the random paths being generated, the water molecule generated is the ground motion as it is being generated. And each time you run, it will be a different snowflake because it is random. But something is similar that I will come to later.
If we increase the dizziness.
Yes, let's do that. Let's make it 15. It makes a much more solid snowflake. So that means the environment is not that supersaturated. So the mean free path is 50. But even if unless it comes very close, it does not stick. So in that case, you get this blocky snowflakes. So you can change the parameters to get different snowflakes. So each time you run, it will be a different snowflake because it is a random walk. But one aspect of this thing is same for a particular set of given distance, that is the random walk and the sticking distance. That is the box dimension of this snowflake fractal. People who knows about the box dimension, who knows about the box dimension here, like fractal dimensions? Okay, so it is a measure of how fluffy the snowflake is. Okay, so the fluffiness,
I mean, fine.
so the fluffiness depends on the these two parameters only. Okay, now let us just remove the random walk points because we don't need it anymore. So once you remove it, now it should look, it is a developing snowflake. And actually, snowflakes develop in this way as you see it here. It is morphologically accurate. It is a very simplified DL algorithm, but it gives pretty good results. And you can take videos later also, I will say. No problem. Also, if I make it business by
process stop? When does this process stop?
The process stops when we qualify a no loop function. So no loop is called when this edge touches the screen.
Yeah, no, but in nature.
In nature, when it drops out of the cloud.
When it drops
Out of the cloud. So
Okay,
so as long as it is in the cloud,
Yeah.
in a supersaturated environment, it will keep on growing. Sometimes it happens that it goes falls from a supersaturated. It is still in the cloud, but it is not supersaturated anymore. The environment. Then the snowflakes actually start subliming.
Okay.
So it also happens. And the snowflakes are not. So this is a specific kind of snowflake. There are many kinds of snowflake. You can see perfectly external snowflake also. If you notice that the first stages of development of a snowflake, these sharp tips does not form. It is more or less symmetrical. And as it goes on increasing, you form these sharp tips. You can see it in real snowflakes also. As it if it is a not very developed snowflake, small snowflake, it is hexagonal. If it is a developed snowflake, it has these lines on it. So pretty snowflakes, we want to take videos of it. So rather, we'll just say that when we are telling the loop to stop, we will also say that okay, save the frame also. Okay. So for the save frame to work, I have to save the file. So I will go here and save the file somewhere, and then run it. So our project is developing, and it looks like this as C developing. And once it develops, it stops. When you go to the parent folder, it was saved in. You see, it has saved the frame.
In what format it is saved?
Okay. Huh?
In what format it is saved?
It is by default saved in TIFF format. You can save it in any format, JPG, PNG. So there you go, Snowflake. You completed it. You can run it as many times as you want with different parameters and get very different results, different snowflakes. These are the snowflakes I drew last night. So all the things you see, these first 4 snowflakes, it has been made in a particular humidity and mean free fall conditions. So they kind of look similar if you see. This is different, and these are all made in again similar conditions. So these all look the same. The fluffiness looks the same. This is not that fluffy. So it is made in different humidity conditions. So all of the snowflakes are unique because the random walk that the particle takes is unique. But the fluffiness depends on your parameters. You can make as many snowflakes as you like to these parameters. So yeah, that's it. I would like to say that processing means a lot to many of us because it was the first language we ever learned. And if you go back and if you like this method, there are a lot of processes, other processes. So far we just touched through the 2D aspect of processing. Processing can also render in 3D by OpenGL. That will be taken by the project tomorrow, next session. So if you like this, if you go back and try to explore it a little bit more, I am sure that many of you will do better processing than at least me in a couple of years, I guess. So yeah, I hope you like it. Snowflake.
Thank you everyone for coming. Thank you, Dr. Bhaiya. I don't think I would have ever imagined attending an offline processing talk. Thank you, Lumia, for recording this. I hope everyone comes tomorrow. See you.